Now, some people, I think, might know this function already. This modulus function, we actually write it like this. Does anyone... Take my sweater off because I'm going to get hot and angry. Right. Does anyone know what this is?
A modulus function.
What was your EAP again? Yeah, absolute is another name for it, but what does it do?
No negative.
Yeah, so how would you define the function? Like, what is its action?
If x is something.
No, come on, no, shh. Go on, Jerry. If x is...
If x less than 0.
Yeah. Hold on. If x is less than 0...
this function equal
yeah.
x, minus x.
Very good.
And equal 0, x. And equal 0 and x.
Okay, if it equals 0, it's 0. Yeah, okay.
0, x.
And if it's more than 0, it's x. So in other words, modulus 3 equals modulus minus 3, which equals 3, as an example.
Yeah.
So this is the definition. Do you want to write this down, KJ, or did you write it down? So I saw a video of Lorraine on a skateboard.
Yeah. She's pretty good.
She is. I was impressed. I was impressed. She sent me the video. I got her message. She said, "Hi, Stephen." I was skating by the camera.
Yeah.
So I asked her maybe the school can buy us a skateboard. We can use it like among the teachers. Just get the class or something.
How about students?
Students can buy their own skateboards. They have too much money, you see. Okay. We got that?
Mm-hmm.
So, how can we deal with a modulus function using algebra? Like, for example, how could we, for example, cancel a modulus function if we had an equation with it? I'll give you a simple example. Like, for example, suppose we had something like modulus x minus 3 equals 2. Then what would the x equal? Well, I hope you can see at least one possible answer. It's 5. But there's actually a second answer. Yeah, very good, Jerry. 1. Okay, and this is kind of easy to see because that will make a 2 and it will also make a minus 2. Both becoming 2 after the modulus function does its job. But maybe for something more difficult it's not as easy to see. We have a couple of ways of dealing with it. Let me show you the first way. So note x squared is also equal to minus x squared because that's equal to minus 1 squared x squared, which is equal to x squared. So in other words, for a function like squaring, does it care if it's a plus or a minus? No, it doesn't. So therefore, modulus of x squared, that's the same as x squared. Why? Because this, you lose the sign, but here you lose it anyways. So it actually, there's no need for the modulus and the square together. You only need the square. So in fact, you have this very useful result. Modulus squared is the same as x squared, and that's actually the key to cancelling a modulus is by squaring it. I'll give you an example using the one we just had a look at. So for example, x minus 3 equals 2. I say if I square it, I don't care about the modulus anymore. Alright, so that means then I can just change this into a bracket. which then becomes x squared minus 6x plus 9 equals 4. So x squared minus 6x plus 5 equals 0. So you get x minus 5, x minus 1. So x equals 1 or 5, which is the same answer we got earlier when we just had a guess of the answer. Same. So this very useful little trick for cancelling out a modulus. Yeah? Okay. But for simple problems, you don't need to go this extreme. Like, for example, if I had, what was it, x minus 5? No, x minus 3 equals 2, wasn't it? For something simple like this, you could actually solve it as follows. You could just simply say, well, x minus 3 has to equal either plus or minus 2, because that's the only way a modulus of something could equal 2 is if that inside piece was plus or minus 2. So then you get x equals 3 plus or minus 2, which equals 5 or 1. So for simple problems like this, it works just fine to look at both the plus and the minus. So you actually have two ways to do it. This way and this way here. There's the two different ways. Okay, so write down what you need to, please, and then we'll have a look at more difficult examples. Can I just have the book for a second, Jerry?
What?
The book, please, just for a second. I want to check how hard I made these. We'll do some inequalities next. Just leave this here for a second. Thank you. Well, I'll give it back to you, don't worry. What's wrong? 10 euros? It's my book, I can take it back.
Yes!
As you noticed at the start of the class, it has my name on it. Stephen Easley Walsh. Now, I actually haven't said yet what the graph looks like, but maybe somebody actually knows already what the graph looks like here. Does anybody know? Yeah, what's the graph like? What shape?
V.
It's a V shape, isn't it? Where this is exactly slope 1, and this is exactly slope... No, come on, wakey, minus 1. Yeah. So I have two more big things to do. I want to look at the graph of more difficult modulus functions and inequalities. Can I continue?
Yeah.
Yep. Right, let's take something like, I don't know, minus 8 x plus 5 plus 11 less than or equal to 3. Yeah? Yeah. Yeah. Continue. So I get minus 8 modulus x plus 5 less than minus 8. Right? Yeah. So then I get this bigger than or equal to this. Now, I have two ways to do this. What is one way I could do this? I could square, couldn't I? Well, let's see. And you know what? Actually, let me open up my graphing program too. That would be nice. X squared plus 10x plus 25 greater than or equal to 1. X squared plus 10x plus 24 greater than or equal to 0. 12 and 2? No. Not 12 and 2. 6 and 4.
Yeah.
Which is going to be here. So it's going to be x less than or equal to minus 6 and x greater than or equal to minus 4. Yeah.
Yes.
Yeah.
Yes.
Yeah.
Sure, the graph is moving like
Like what?
this.
What the heck is that?
Like,
Tis not. Tis not, my friend,
No, no.
because I'm just graphing this quadratic.
oh, okay.
Yeah. Well, let's check the answer here. So let me just type this in. No, I opened the wrong program. I wanted my graphing calculator, my graphing program. There we go. Just give it a minute, okay? There we go. Okay, so let's see what we have. Minus 8 x plus 5 plus 11 less than or equal to 3. Okay? So what I'll do is I'll graph this, zoom out, less than or equal to 3. Now let me just add in the line 3. What's that? Y equals 3, isn't it? There. So less than or equal to 3 happens here and here. So my answer should be smaller than minus 6 and bigger than minus 4. That is when this function is smaller than this. From minus 6 to the left and minus 4 to the right, which is exactly what I said. So squaring does work. But there's another way to do this one. Does anybody have any other ideas on another way I could do this?
Plus minus
Bigger.
plus minus 1.
I know what you're trying to do, but you're doing it wrong. So it's from this line.
Yeah.
We want to try and solve x plus 5
Bigger and
bigger than or equal to 1.
1. Yeah. Bigger than or equal than minus and or plus.
No.
You open the modulus, you have to change the sign.
How do you open a modulus?
I don't know, just disappear and then change the sign.
Oh, yeah.
So you're saying I should do this, x plus 5 greater than or equal to plus or minus 1. Yeah,
but
right,
you
no.
have to change the sign because you open it.
Yeah. How to
Less than and equal minus 1.
Yeah, less or equal to.
So you're saying x plus 5 greater than or equal to...
No, less or equal to
Yeah?
1.
Minus
Plus minus 1.
No.
1. Less than equal less than.
Bigger.
Anyways, it doesn't matter, you're doing it the wrong way. So, the way... Now, I'm not saying that won't work or it'll get you the right or wrong answer. What I'm saying is the way to approach this is...
Times negative.
No.
Okay.
You look at this and you say, well, if x plus 5 is positive, or in other words, if x... Oh, let me write that again. If x plus 5 is positive, or in other words... Oh my goodness, what's wrong with my pen? I'm tired. Or in other words, x is bigger than or equal to minus 5, then do I need to write the modulus sign? No, because it's positive, so what will it do? Nothing.
No.
So I'll get x plus 5 bigger than or equal to 1. So x is bigger than or equal to
Minus 4.
minus 4.
Yeah.
But don't remember, I said x, or don't forget, x is bigger than or equal to minus 5. So how can I put these two together? It has to be bigger than minus 4, but also bigger than minus 5. How can it be both? Bigger than minus 4. If you have a number which must be bigger than minus 5 and bigger than minus 4, it can only be both if it's bigger than minus 4.
Yeah.
So minus 5 is here and minus 4 is here.
Yeah, so bigger than means to the right.
Yeah, so it's 5.
It's 4.
It's
Because
4.
it's minus. 5 is...
Minus 5 minus 4.
Okay.
Yes. Okay. Now, if x plus 5 was negative, or in other words, if x was smaller than or equal to minus 5,
Amen.
then that means what would the modulus function do? It would change its sign.
Yeah.
So then you would have minus x plus 5 greater than or equal to 1. Which means minus x minus 5 is greater than or equal to 1. Which means minus 6 x must be smaller than, no, yes, x must be smaller than minus 6. But x must also be smaller than minus 5. So here's the number line, minus 6 minus 5. How could x be smaller than minus 6 and smaller than minus 5? Smaller than minus 6. Now, are these two answers the same? They are. No, they're not. Oh, bigger than minus 4, smaller than minus 6. Bigger than minus 4, smaller than minus 6. They are. So you have two methods here. So you have the squaring method, and I don't know, what would we call this method? The case method, where you look at each case, the positive and the negative.
It is just random name.
I like plus case method, plus minus case method.
I mean, do we see that term in as well?
No, I just made it up right there.
Teacher, do we write the first step compared to 0?
Nah, you mean could you just start here and here? That's fine.
Start from x plus some small particle.
I would start from here. Yeah, I would write all of this down.
Also.
Yeah, all of this. Yeah. I do want one, but I ate a lot of takeout last night, so I shouldn't. You had what last night?
Donut.
Just a donut?
Nutella donut.
Good deal.
At 2 a.m.
Oh.
And then I sleep. But I really did nice.
So let me see. 2 a.m. donuts, 7 a.m. chocolate rolls, 11 a.m. Coca-Cola.
9 a.m.
Oh, 9 a.m. Excuse me.
So
Of course, what am I saying? 7 a.m. That's
How
right.
did I say that?
Still asleep at that time.
Yeah, of course.
Are we ready? Yep. Okay. So the next thing I want to do, or the last thing I want to show you, but there's two ways to do it, is how to graph these functions. So let's say I have y equals, I don't know, 2 modulus 3x plus 6 plus 1, or something like that. There are two ways to graph this. The first method is what you learned in the last class, using the transformation. What you do is you rewrite it like this. maybe I'll actually write minus 2. So remember what this one does. This one goes that way. This one here contracts. This one here will move it to the left. And this one here will move it up to the left, because is this confusing with the two minuses? I was trying to make it easier. It's confusing? It's okay. Plus left minus right, but I put a minus here so that minus left and plus is right. I don't forget it. I was trying to make it easier, but I can see I'm confusing you. But no, forget it. Forget it. Plus, so left. Okay. And if we call fx equal to modulus x, then we just have this function, y equals 2f 3x plus 2 plus 1. It's the transformation. So, transform. That sounded like Optimus Prime there. Autobots, roll out. Okay. See, Sean is transforming, aren't you? Transforming into a truck or a motorcycle. Anyways. And just remember, I'm Optimus Prime, okay? Right, continuing. So, let's start with the 2. What will the 2 do here? It'll just stretch it by 2 units. So, for example, here was 1, 1. Now it'll be 1, 2. Minus 1, 2. And here was 1, 1. It'll now be 1, 2. In other words, the graph just gets stretched up like this. What's the effect of the tree? It was contracted 3 units. So instead of being, for example, 1, 2, it would now be 1/3. Yeah. So in other words, it gets squished. It looks like it's getting squished right in. The plus 2, we'll move it to the left. And then the plus 1, we'll move it up. So you'll finish off with a graph here, where this point is, minus 2, 1. Now, let's just draw that in the graphing program. See what we get. Can you call out the function? What was it originally? 2 absolute
3x plus 3.
3x plus 6 plus
1.
Okay. Did I say minus 2? I did. And did I say 1? Yeah, that looks like 1, doesn't it? Whoa. Yeah, that's what I drew. Now, that's one way to do it, and that's fine. But if you want to be a little bit more accurate, perhaps, or a bit more algebra, you can just draw it the way that you learned how to draw it in semester 1. So what you do is you first find the x roots. How would you find the x roots here? You would have to solve this. 2, 3x plus 6 equals, plus 1 equals 0. So you get this. Now, I won't bother to square it. Why is there no point in squaring this? Why is it pointless to try and solve this? I know it won't be solvable. Well, it's impossible for this to be negative. So I know that the quadratic I'll make will have no roots. It'd be a waste of time.
Yeah.
So there's no roots here. 100% sure. This is always positive by definition. It can never equal a negative number. It'd be, if you don't trust me, and that's fine, you can square it, make the quadratic, and see for yourself it'll have no roots. Okay. Number 2. I could find the y-intercept. How do I find that? Where it crosses the y-axis. Yeah, go on. Oh, come on, children. You know this one. X equals 0. So y equals 2 modulus 6 plus 1, which equals 13. So we know so far this has no roots and it crosses at 13. Okay, that's not a lot. Lastly, we should find the vertex. Remember what the vertex is? The turning point, the minimum. How do you find the minimum? Well, if it was a quadratic, what would you do? If it was a quadratic, what would you do? Derivative. Or? No. Think back to semester 1. Completing the square. Yeah. I thought you said square, the completing. Completing the square, yes. Completing the square. Now, why would I not use the derivative? Well, because I never told you what the derivative of the modulus function is. Did I? No.
0.
It is not.
Oh.
Yeah. So, because I didn't tell you the derivative of the modulus function, we'll have to complete the square. Now you realise it's actually already in completed square form, so to speak. You might be saying, why is that, Stephen? Well, compare it to this. Can you see the similarities?
Yeah.
Do I have a number? Yeah. And a number at the back?
Yeah.
And is this piece guaranteed to be positive?
Yeah.
So, yeah, no, it's exciting. It's already in completed square form. So, do you remember how do I get the vertex from this form? Yeah, what equals 0 exactly? 3x plus 6 equals 0. So x equals, in this case, minus 2, and y would equal 1. So I know the vertex is here at the point minus 2, 1. So let's go back to my graph and see, is that the same? Does this cross at minus 2, 1? Yes. Let's zoom out. Does it cross at 13? Looks like a 13 to me. So you have two methods for graphing this. And finally, how would you graph a composition of a modulus and a non-modulus function? So for example, suppose I have something like y equals modulus of x squared minus 3x plus 2. How would I graph this, a function like this? Any ideas? Dudes? Will I tell you then if you don't know? What you do, first you just graph the non-modulus part. What the heck? Did I type in a cube?
Yeah.
Awkward. Okay. First you graph the non-modulus part, and then what does the modulus what will that do to the quadratic? Well, when it's positive it does nothing, and when it's negative
It becomes positive.
it just becomes positive. So on the graph, this negative piece, and only this negative piece, gets flipped up. So if I go back here and just put an absolute around this and now graph it, we should get something that kind of looks like a W, because the negative part gets flipped up to the positive. It's not too difficult. The modulus makes everything positive, so it's like reflected, except it only reflects the negative part of the graph.
Again, it's cubed. What happens?
Same thing. Will we stick in a cubic? Let's put in x minus 1, x minus 2, x minus 3, and graph this. And then absolute. Right, so before I graph it, I just want you to picture in your mind what would happen. Can you see it? So this, I think, would flip up, and this would flip up. So the graph should go down, normal, normal, and up. So it'll really look like a W now. Is it there? Yeah, it does have a bit of a backache about it. Okay, got that? Yeah. So what do they like to do in the exam for the modulus? The most common question they like students to do for modulus is to make the graph. But they often want you to use this method. How do you know which method to use? It depends on what they ask for. So if they ask you to graph it showing clearly the roots, the intercept and the vertex, and they obviously want you to do this method so you can clearly get the exact point. But if they just ask you to sketch, a rough sketch, then you can do it this way. It depends on how many marks are going for the question and what language they use. Often I find though they want you to do it this way mostly. And sometimes they give you things like this, and sometimes they give you inequalities and equations, but most of the time it's making a graph, which is not too difficult. So it is actually a good question in the exam. Yeah. Okay, so if you can try these for a few minutes, and then you can take a break after you try some of them. That's the last lesson of the mappings and functions chapter. After that, we are going back to calculus.
Yeah.
Can I close this? Chrissy, can I close this? Yes? Yes? Okay. KJ, Monica, yeah?
Teacher, what does the version mean? You have many versions.